So thanks for coming in the last week for this lecture. And I'll try to be short. I don't want to keep you too long into the evening. And so today I plan to go through a couple of things. They are kind of interconnected to each other. And that's why I have put them all together in one place. And we'll start with what is called principal component analysis. Then we'll move to kernel principal component analysis and some other visualization tools. Then once we have got an intuitive understanding of PCA, that kind of leads a way to encoder decoder architecture in machine learning. And then we'll briefly touch on encoder decoder, move to variational autoencoders, and just hint on GAN, like what is generative adversarial networks. Right, so a lot of stuff we'll be covering, but mostly we'll be giving intuitive understanding and not really going through all the math, etc. So yeah. Okay, right. So one of the main motivations behind principal component analysis is reducing the dimension of the data. Now, dimension of the data is an interesting part, and it depends how we define it. Usually, if we, let's say we have got multiple sensors. So for example, we have got house, and then we have got, it's not going. Yeah. And then we have got multiple sensors here, 1, 2, 3, 4, all trying to measure, let's say, carbon dioxide sensors. Now, if you have got 4 sensors, on any given instant, you will have 4 readings, right? So sensor 1, sensor 2, sensor 3, and sensor 4. So let's say 200, 250, 230, 200 again. That is on the fast. Let's say you are collecting data every hour. So this is one set of data. And remember that we have discussed it briefly previously. Always data is assumed to be a column vector, right? So that's why this is one data, a vector. And in the second hour, you get some more readings, and similarly, you can stack hour after hour after hour of readings. Now, this is called a data matrix. Now, the data matrix will have 2 dimensions. So, M cross N, right? So, this is M and this is N. So, once you are put in this way, you can have a lot of intuitive understandings here. So, first of all, the number of sensors determines how many rows are there, right? So, if you have got 4 sensors, you have got every column will have 4 components, right? So, there will be 4 rows. And if we take the example of, let's say, multispectral satellites, I forgot the exact number. I think Sentinel-2 has got 11 channels or 12, like that, which means there are 11 or 12 sensors. So every reading from Sentinel-2 is of dimension 12. So in this kind of data, you have got, let's say, 4 sensors or 12 sensors, whatever. So that number of sensors determines the dimension of the data. And the more data you collect, it just increases the N, the size of the data matrix. So the data matrix has got 2 parts. One is M, which is fixed based on the measurement campaign. The other one is N, that depends on how much data you are collecting. Now you have got M dimensions, and then you have got N data, and you can collect hundreds and hundreds of data points, and that's all fine. Now, if you remember what we discussed previously, this is data which dimension is this example 4, which means if this data is following Gaussian distribution, your Gaussian distribution will have a mu vector which will be dimension 4 cross 1, and Gaussian distribution has got two parameters, right? The mu vector, the mean vector, and the covariance matrix, and that will be of dimension 4 cross 4. Right. My point is that if your data dimension is higher, then to represent that data, you need bigger and bigger covariance matrices. And for example, let's say you have okay, let's now come to the other extreme, image processing. So let us say you are dealing with images, and each image is, let's say, 2 megapixel. 2 megapixel means every image has got 2 million data points. If there are 2 million data points, it implies that to represent that data statistically, you will require a covariance matrix whose dimension is 2 million cross 2 million. And that is why it gets complicated in terms of memory, in terms of computation, because most processes in statistical signal processing will involve covariance matrix. Hence, the bigger the dimension, just dealing with things in signal processing or data processing gets much more complicated. Number one. Number two, the second thing is that, okay, the question is what is wrong with high dimension? The first thing that is wrong with high dimension is that the higher the dimension, what happens is that your covariance matrix becomes bigger, which implies that doing any kind of data processing will involve way more amount of computation and saving of data. So that's one first problem. Second problem is, let us look at this this setup. So we have got 4 sensors, and in a room, even if it is a big room, having 4 sensors for just carbon dioxide, well, you don't really expect that they all will be reading very different readings, right? So mostly, whatever all these 4 sensors will be reading, they will be related to each other, right? So when you have too many sensors, or when the dimension is high, there is also the issue that maybe not all the sensors are reading independent information. Or in other words, maybe not every sensor is adding extra information. So that in technical terms is called correlation. So the sensors or the dimensions might be correlated. If they are correlated, then it implies that even though there are 4 dimensions, maybe 2 dimensions are good enough to have all the information, because it depends how much information is available to be collected, to be measured. If the information is not too much, then maybe just 2 sensors are enough. So, but again, that is a guess. How do you find if they're enough or not enough? You take the data for a high dimension data set. Like, for example, let's say in this particular case, okay, you put 5, 10, 12 sensors, whatever you have, like try to oversample. After oversampling, look into the data and look into its correlation matrix. The correlation matrix will guide you to find out, okay, how many sensors are actually optimal. So that's one of the things. So high dimension has got 2 problems so far, right? Number one, it makes computation very difficult. It's memory heavy and all those things. Secondly, sometimes if the dimension is too high unnecessarily, it has got correlated data. So basically you are spending extra computational power, but you're not really getting extra information. So you are wasting your computational power. The third thing is that when you put an extra sensor, so extra dimension means extra sensor. When you put an extra sensor, every sensor reads 2 parts. First part has got information. The second part has got noise. So every sensor, every data will have some amount of noise. Now, let us say you have got extra sensors than what is required. So your sensors, your data is correlated, which means that you are putting extra sensors. So the extra sensors are not collecting an extra information, but they are always collecting extra noise. Hence, just adding more sensors. So this is one of the cases where more is not always better. Right? So you have to be very careful how many sensors, how many bands you want to use. Because when you use extra sensors, extra bands, if they are correlated in terms of what information you are seeking, then it will imply that yes, you are wasting your computational resources, but also you are adding extra noise where noise could have been avoided. Right. Okay. So this is sometimes called the cost of dimension. So high dimension is troublesome, and we have discussed all those things. Okay. Yeah. So now the question comes. Okay, you have got some data, and maybe your placement or choice of sensors was not optimal, or maybe you are trying to make a generic sensor. For example, Sentinel-2. Sentinel-2 has chosen those sub-bands based on a lot of scientific evidences. Now, if your application doesn't require all the sub-bands, they can reduce the data or the sensor there, right? So the data will come to you. You have to make sure that, okay, from that correlated data, assuming that the bands are correlated, from that correlated data, how can I reduce my dimension and not lose information? Right? So as I was saying, we have got information, data has got two parts, information and noise. So is there a way by which I can reduce my dimension, thereby making my computation easier and faster? At the same time, make my data uncorrelated, which means whatever data you have, they have got enough information, and you discard all the noisy part. Now, that's principal component analysis has got multiple ways of looking at it. Even though the process is the same, philosophically speaking, mathematically speaking, there are different angles at from which you can look at PCA. But we are just looking at one of the ways of looking at PCA. There are always other ways of looking at PCA as well. But the process is the same, of course. Right. Now, how to reduce the correlation of dimension? Because we are reducing correlation, so maybe we should look at correlation matrix, right? Okay, and roughly speaking, what we want to do is that we have got, so let's say we have got x, which dimension is n cross 1. I want to convert that to some x tilde, which dimension should be k times 1, where n is much larger than k. So I want to reduce the dimension of this original data x. Right? How do you do that? And we can use the eigenvectors of the covariance matrix of this data. So I will not derive those things, but this is what PCA involves. So what you do in PCA is you take the data. From the data, you find the covariance matrix. From the covariance matrix, you find the eigenvalues and eigenvectors, and that will give you everything that you need. Okay, so let's go step by step. So we have called that data matrix. We haven't named it anything. So okay, let's name it D. Okay. Yeah. So let's say you have got dimension. Sorry, you have got the data matrix D. It has got m rows and n columns, right? What does it mean? It means that the dimension of the data you are collecting is n. So if it is corresponding to number of sensors, so your field has got m sensors, right? And what does n mean? N implies how much data you have collected. Let's say you are collecting every hour and you have collected over 1 day. So n will be 24, right? Then what you do, you subtract the mean. So you d minus mu d, and you find its covariance matrix. Now covariance matrix formula for discrete variables. Of course, for continuous variables, it's a bit more complicated. It has got integration, etc., etc. For data matrix kind of thing, it's quite simple. So, what is covariance matrix of D is equal to, so here the dimension is m, right? So it will be 1 by m minus 1, and d minus mu d, d minus mu d transpose. So yeah, so d minus mu d, the dimension will be m cross n, and transpose will be n cross m. So the dimension of the covariance matrix sigma is m cross m, right? Now if you find its eigenvalues and eigenvectors, you will get m eigenvalues and m eigenvectors. So I think we have, yeah. So you have got your data matrix and you have converted into sigma d. Sigma d is your let me remove this one. Yeah, sigma d is your recording or not recording? Yeah, actually recording. Okay. So sigma d is your covariance matrix. Now from that you do eigen analysis. Eigenanalysis will give you your lambdas are usually used to represent the eigenvectors. So if there are m cross m, right? So this is happening m cross m. So you will have m number of eigenvalues and m number of eigenvectors. So sorry, lambda are used to represent eigenvalues. So you will have lambda 1, lambda 2, lambda m. Always it's a column vector, and then accordingly different ways to represent that. Let's represent every eigenvector corresponding ones as e1, e2, em, right? So each of these vectors has the dimension of m rows and 1 column, right? So total this matrix is also m cross m. Now comes the magic. If your data is correlated and then you plot these lambdas, right? So you just plot them. Is your index, and here you. So usually it's better to plot cumulatively, but even just plotting individual ones is also fine. Lambdas. So usually the first few would be quite high, and then it becomes quite low. So this again, it's a thumb rule. It's not a rule that every time you do eigenvalue analysis of covariance matrix, you will see the same trend. But mostly, when you take a data set and do its, find the covariance matrix and then find the eigenvalues and plot them, mostly bunch of them will be very high and rest of them will be very low in value. That actually implies this bunch, let's say the first 10 eigenvalues are very high. It implies that only 10 variables are actually uncorrelated, or only 10 variables have most of the information. So if let us say 10 of those variables, sorry, you have got 10 eigenvalues which are quite high, and beyond that they are quite low. What we can do is you choose, okay, let's replace k with, sorry, 10 with, let's say p eigen values are very high. Then you pick up p, the first p eigenvectors. So you make e matrix in which E1, E2, and EP. So you pick P eigenvectors and stack them together to make this E matrix. It's also called PCA matrix. What will be the dimension of this one? Because every E has got the dimension of the original dimension, M, right? So it will be M cross P. Now the process is very simple. So you had your data matrix D. To convert that, so data matrix D had the dimension of M cross N. So you just want to reduce the dimension. You don't want to reduce the number of data. So you expect to have a matrix again, a smaller data matrix. Let's call it PCA data matrix, which dimension would be P cross N, right? So what you do is you pre-multiply that with the transpose of E. So E transpose times D, that will give you dPCA. So E dimension was M cross P. So E transpose dimension will be P cross M, and D dimension is M cross N. So the dimension of dPCA will be P cross N. Right? Now you have reduced the dimension. So this will look like smaller ones and so on. But again, same number of data points. So every data dimension wise has been reduced now. Now, this is principal component analysis. Very simple. It doesn't take much to explain it. Take the data, make the data matrix, subtract the mean, find its covariance matrix, find its eigenvalues and eigenvectors, plot the eigenvalues, look how many eigenvalues are necessary, and then pick up those number of those corresponding eigenvectors, make the principal component conversion matrix, pre-multiply your data matrix with the conversion matrix transpose. That's it. Okay. Now, the resultant, this dPCA, you see here, let me get a bit fancy, make a red color. So this thing, now the data here, they are guaranteed to be uncorrelated. That's the first thing. So in this one, the dimensions are not correlated at all. So that's the first thing you get. Now, of course, the second thing is that you have chosen only a few eigenvalues. So already you have reduced the dimension. Now, when you reduce the dimension, if you reduce the dimension to 3 or 2, then you can then every data point becomes a value with 3 numbers only. You can plot them as coordinates and you can visualize them. So another benefit of PCA is that you can use PCA to visualize them, because once the data dimension is 3 or less, you can plot it. You can visualize. So sometimes what happens, okay, let us say even though you have found that, let's say, the first 9 eigenvalues are quite high. So ideally speaking, you want to consider the first 9 eigenvalues. But just for visualization purpose, you can convert that using just the first 3 principal components. And then you can plot that in 3D plot, and then you can see. Now, what does visualization bring? Now, visualization is extremely important because when you are applying or developing any kind of data processing on data, you have the inherent assumption. You assume that the data has got some kind of structure. The structure may not be visible in the immediate way you look at the data, but in some hidden dimension, data has got structure. Because if the data has got no structure in no dimension, no amount of fancy algorithm can actually do anything. So that is a hidden assumption in every data processing task, that the data has to have some kind of structure. Now, tools like principal component analysis and so on, we'll discuss a couple of more of these things as well. They help us to just validate, does the data has got structure? I'm assuming that, okay, I want to separate out forest land covers from ocean land cover. But is it even possible? So one quick thing can be, okay, you take the data and then plot into 3 principal components. And if they cluster together, so you see that, okay, the points belonging to forest cover, they are clustering on one side in that 3D space. and points corresponding to, let's say, ocean, they are clustering in the other side of the space. Then, at least at data level, the data is separable. Now it's up to you to find out how you do the separation. Right. Okay. Yeah, we have seen all these things already. Now, one of the fast applications of PCA in like the modern times, it was for face recognition. And what you see here is something called eigenface. So eigenface is basically you take less number of principal components and then you recreate the face. And the reason I wanted to mention it here is we have just discussed that you collect the fast couple of principal components, or you collect the eigenvectors corresponding to the largest couple of eigenvalues. That is good, but that sometimes in some applications that may not give you the most important information. So for face recognition, they found that the first two principal components, even though they corresponded to the two largest eigenvalues, they were not very helpful in recognizing the face. And then after lots of heuristic studies, they found that the first two principal components, physically speaking, they are representing the length and the width of the face. And the length and the width of the face doesn't really have much information that can help one to recognize the face. The recognition comes from things like, okay, how separate are the two eyes, or how is the triangle, two eyes and nose, how does that look like? Now they found that the lower principal components correspond to those kind of things. So that's another benefit that principal component brings to the table. Mostly, not always, mostly principal components correspond to some physical thing. So what in philosophical terms is called phenomenology. So phenomenological importance of principal components is quite good. So that also makes them algorithm of choice, and that's why, like, they were invented roughly a couple of years after First World War by a guy called Carl Pearson, one of the father figures in statistics. Even now, you look in Google Scholar, you will find lots of papers getting published every year where they're using PCA. So it's an extremely powerful and versatile algorithm. Okay, now coming to the application in Earth observation. So what PCA brings to table? Number one, it reduces the dimension without losing information. Number two, correlation is minimized. And number three, variance is maximized. So whatever few number of components you are left with, they capture a lot of variance or information in the data. So for example, depending on what sensors you have, because multispectral may have dozens of bands, and hyperspectral may have hundreds of bands. So then the data processing becomes quite hectic. So you can use PCA to reduce the dimension of multispectral and hyperspectral data. Sorry. And it can also be used as a pre-processing step in some of the change monitoring algorithms. And there are also a lot of applications where they use principal component analysis, and the principal components are used as features, and then they are fed to a classifier. That's also quite common in application. And I have given examples. They're not only examples, but some of the examples in EO of the use of PCA. Right. Now, coming to the limitations of PCA. So nothing is ideal, right? Like every algorithm has its own limitations. PCA assumes that information is captured by covariance. So that covariance matrix for which we did the eigen analysis, PCA assumes that that has captured all the information that is there in the data. That's well and good, but that's not always true. A couple of cases. Number one, first of all, covariance matrix is good enough to capture the statistical properties if the data's distribution is Gaussian. If the distribution is not Gaussian, then covariance matrix is not good enough. So it's one of the cases. And secondly, we have seen that PCA involves only linear processes. Like you take the matrices, you multiply the matrices, and then that's it. Basically, matrix multiplication. So if you have an algorithm that has got only matrix multiplications in that, roughly speaking, that algorithm is linear. There are small other rules as well, but more or less, if the algorithm only involves matrix multiplication, it's a linear algorithm. Now PCA, we have seen that it only has got vector and matrix multiplication. Hence, PCA is a linear process. It has got its own merits and demerits. The merit is that the processing is very simple. Computers are optimized for that kind of processing, so it is very efficient to implement in digital computers. The bad thing is that linear processes don't really capture all the intricacies of natural phenomena, so that can be one of the things. But in a more abstract sense, sometimes what happens, your data may look more interesting when you transfer to a nonlinear space. This is simple example you see here. So what it shows is you have got a linear data, this one, and then it has got two classes. This is the class 2, and then this is class 1. So C1 and then C2. Now they are distributed in such a way that there is no way you can have one boundary separating them properly. You need two boundaries. So you need this boundary and this boundary. When you have got two of these things, this is not a straight line. It is not a linear separation. So there is no linear boundary that can separate these two classes. What you can do is an interesting gimmick here. So you can, it is one dimension. Let's call it X. You can create a 3-dimension space from just one dimension. So what you can do is that every point you map into 1, x and x square. So for every given point, let's say the point is 2. This is 1, 2, and 4. So you find that coordinate and that becomes the new point. When you plot or when you transfer this data into this new dimension data, so this is basically the same data, but you have passed it through a nonlinear transformation. Then the same line now looks like this. And in this new nonlinear mapping based space, a plane is able to separate the two classes. So it shows that in the naive space, you could not have a linear separation of the two classes. When you transfer that to a nonlinear space, a simple linear boundary could separate them. Which means that if you can transfer the data to a nonlinear complicated space, your algorithms may become easier. Because now, instead of a complicated boundary, just one linear boundary is good. Now, let's hold that thought. Now, how is it possible? Because the moment, so we just discussed that we don't want big dimensions. We want things to be small dimensions. We like spent already almost 40 minutes just discussing that. The big dimension is a cost, the cost of dimensionality. So we're using PCA to reduce dimension. Now we are saying that there can be some benefits of taking to a much higher dimension. Now, the benefit may be whatever, but when you go to a higher dimension, it implies that computations will become higher. Because in this dimension, let us say, you just have one line, right? One number. So you want to multiply two things, just one multiplication. In the 3-dimension case, even though one is constant, still multiplication will involve two multiplications. How is it better? Now, that is where something called kernel trick comes to picture. What it says is that, okay, you can go to higher dimension, but there is an inherent issue. If you are thinking that, like, the benefit that was brought here, is this a linear boundary? So if you are thinking that all your algorithms in the higher dimension are going to be linear, let's assume that, because otherwise there is no benefit. If that is the case, any linear operation involves what is called dot product or multiply and accumulate, MAC. So even though your algorithm can be complicated and elaborate, the actual core operations that is required are always MAC if they are linear operations. Now, the question is that what kernel trick brings to the table is that it says, okay, you may go to a very high dimension, but if you can find the dot product in the high dimension by having something very simple calculation in the naive dimension, then that's fine. You are actually doing operations in a very high dimension, but the actual calculation you have to do is less because a dot product there may be represented by a small operation in the naive dimension, and that is called kernel trick. So this is just an example. And yeah, K, mostly that operation that represents a dot product in high dimension is called the kernel. So let's say kxy is that operation, and this is how you calculate that, x transpose y square. So it is not too bad. It's still a MAC operation, multiply and accumulate, and a square operation. That's fine. But if you expand that, you get this. Now, what is this exactly? So this is x1 square, x2 square transpose times y1 square root 2 y1 y2 and y2 square. So it is as if you have taken both x and y to a higher dimension. So your x has been converted to this column and your y has been converted to this. So from just one number, x and y, you are creating these three-dimensional vectors. But when you come to the dot product of that, so this is basically a dot product, you can find that just by finding x transpose y whole square. So even though it is finding dot product in a much higher dimension, the actual calculation required is just the kernel, which is much simpler. Okay, let's not spend too much time here. Now, the gist is that this is a trick which helps you to handle data in a very high dimension and thereby develop quite elegant algorithms. But the actual calculations required are not prohibitively bad. So when you put kernel and PCA together, so let's say, okay, you say that you can go to a much higher dimension. What about finding principal components in that higher dimension? And that is called kernel PCA, kPCA. And we'll see in the example that we have how kernel PCA sometimes can be very interesting. So data points which are not separable in the naive or simple PCA, kPCA can many times do some interesting tricks, right? And yeah, and kPCA is kind of similar to your multi-layer perceptron. So now we have seen a couple of things. We have seen PCA and we have seen kPCA. In both of them, you take some data, it is creating another data set. So it is reducing the dimension, it is reducing the correlation, and the new data set is uncorrelated and of lower dimension. And one spin-off is that you can also reduce it to 3 dimensions and visualize that. So visualization is not the primary goal in component analysis methods. But let us say if our goal is only visualization, I just want to visualize. I have got a high dimension big data set. I want to visualize if they follow any kind of structure. So there are a set of algorithms that are used only for visualization. So when we say visualization of data, you want to see the structure, that if the data has got any structure in some dimension or not. So, but the naive data that you have collected may be in a high dimension. For example, your Sentinel-2 data, 12 dimensions. We human beings cannot see 12 dimensions, so we have to reduce that to 3 dimensions, let's say. So visualization has got very distinct aim. The aim is that you reduce the dimension, but you try to make sure that the structure of the data doesn't get affected. Now, then comes the question, okay, what do you mean by structure of the data? So structure has got two parts. One is local structure and one is global structure. And we want to preserve both of them. So we want to preserve the local structure. And if you think, if you go deep, what is local structure? Local structure is defined by individual points, right? If you make sure that every point and its nearest neighbors, they remain the same points nearest neighbors in the new dimension data set, then mostly the structure is going to be remaining intact, right? Because ultimately your structure can look something grand, but if you go deeper and deeper, structure at a point level is basically how every data point relates to its neighbors. So that's the first kind of visualization trick. It's called LLE, locally linear embedding. So what we do here is that, let us say you have got 100 points in 12 dimension, and you want to convert that to 100 points in 3 dimensions. So in 3 dimension, you start with 100 random points and try to correspond, okay, this point correspond to this point and so on. Now you try to find out, okay, point 1, who are the nearest neighbors? And for point 1 in the high dimension, who are the nearest neighbors? You want to preserve the first n nearest neighbors and also how far they are from each other, right? And if you preserve that, then the local structure is preserved, and that is what you do in LLE. So of course, it will not be the case when you randomly pick the points. So you iteratively change them, and over iteration, it finds the most optimal choice of points in the 3 dimension. Now, just finding the nearest neighbors may not be enough. Sometimes it is not just the distance that matters, it also matters how are you related, right? So that is why just finding the Euclidean distance to measure the nearest neighbor is not enough. There are other ways by which I think we have discussed different distance matrices, right? So one of the ways in which you can make it even more powerful than simply using Euclidean distance to find the nearest neighbors is by putting one distribution on each point, and then you find, okay, from this point, how far is the other point? For that, you find out the Gaussian distance from that point, and there are different names for that. One of the name for what we are measuring is Mahalanobis distance, but basically it's like you take that point, subtract from the other one, take it square, and divide it by a sigma value, and take the exponential. It's the same Gaussian distribution formula, but instead of mu, you replace that with the other point. Now, in the smaller dimension, you don't follow Gaussian distribution. You follow what is called T distribution, and your goal is to make sure that the distribution of a bunch of points in the high dimension and the distribution of the same bunch of points in low dimension, they are as close as possible. Now, the distance between two different distributions, you cannot use Euclidean distance, because distributions actually don't fall on Euclidean space. So the usual way to find distance between two distributions is something called scale divergence. It's other measures as well, but scale divergence is kind of the usually chosen way to find distance between two distributions. So you use that, and same process. You iteratively try to make sure that the scale divergence of every bunch of point is minimized, and then you end up with something that is in 3 dimension, but it is representative of the structure of the data in high dimension. So you can actually look at that and see if there are some structures. Okay. Now, just let us revise quickly PCA. So what does PCA do? It compresses data such that maximum variance is preserved. And why variance? Because variance, if it is Gaussian distribution, variance does represent information. Now, the second question is, once you have found the PCA, principal components, can you get the original data back? Let's go back to the process the steps we developed for doing PCA. What is it? Yeah. So this is what you have used to find the smaller dimension data, right? And you can always do the reverse multiplication to get the full dimension data. So of course you will lose some information, but still you will do a pretty good job. And that's exactly what they have done in this eigenphase, when they have tried to use a couple of principal components and then try to recreate the whole phase. So principal component analysis has got actually two parts. Number one, from the high dimension data, you can find the principal component dimension data, which is low dimension. And you can use the low dimension data to project back the high dimension data. So yeah, and PCA has got matrix multiplication, and matrix multiplication can be represented or can be modeled as neural networks. So you can have principal components. You have got D, and then you have got DPCA, and from that you can also project back D. Now D has got high dimension. You got some matrix multiplication, mult, and then you got low dimension, and again some mult, and then high dimension. Now this matrix multiplication can be neural networks, so can have so on, and similarly, so on. So you can actually design a neural network, of course, without the nonlinear activation nodes, only linear, and you can design it and train it to make a PC. So that's also possible. And when you do that, it looks like this. You have got an input, and then you have got a compressed bit, and you have got the output. And this thing has been existing for a while, but only recently, like a couple of years back, when people started having algorithms like generative adversarial network and things like that, it became quite revolutionary, because usually neural networks are taken to be directly finding the class boundary. So they fall into the type of algorithms called discriminative machine learning algorithms. So they can find the discriminating boundary directly. The other bunch, just we have discussed this before, but the other bunch of algorithms are called generative algorithms, in which you look at the data, you assume that there is a statistical process behind the scene that is generating the data. And the better we can understand that statistical model generating the data, the more we can understand the data and do all kinds of things. So there were two very distinct types of machine learning algorithms. the generative and the discriminative. And neural networks were classically the discriminative type of algorithms. With this advent, because once you can use neural networks to do this thing, you are actually doing two parts. Number one part, you are encoding high dimension data to a low dimension. In the second part, you are taking the low dimension part and making the high dimension actual data. So basically, there is encoding and decoding going on. Now, the decoding part can be made to create new data. And that is when neural networks started to act like generative models as well. And that was the most revolutionary part in the machine learning, history of machine learning developments. One of the most revolutionary parts, actually. Suddenly, the distinction fell apart. Neural networks can be both discriminative and generative. And once neural networks can be generative, they can start replacing statistical methods. And that is exactly what has happened. Right. So encoder and decoder networks, they're very similar to PCA. Only difference is that unlike PCA, they have also got the nonlinear nodes, making them even more powerful. Yeah. Okay. Right. One difference. So this is also a kind of machine learning algorithm now, encoder decoder, that is similar to PCA, but there is a subtle difference. If you remember, we have discussed some machine learning algorithms. In that, usually we do classification or regression. In both of them, we try to model a function by machine learning algorithms. If you remember, we discussed universal approximation theorem, which told that neural networks with just one hidden unit can approximate any function. Why was it important? Because machine learning tasks can be either regression or classification, broadly speaking, and both of them can be represented as a function. And if something can model any function, then it is good enough for a wide range of machine learning challenges. Now, the difference here is that, so in a function kind of modeling, you need an input function and output. So you need the input data and you need the expected output data. In this encoder decoder kind of networks or algorithms, you don't need that. So what you are trying to do here is your input is your data. Your output is also same data. So you are trying to design something which can compress and decompress and create the exact input that you have given it. So you do not need the kind of training data sets. So training data sets always had a label and feature. And if you remember that small CNN code that we have developed. In this case, you don't need a label. Just the data itself is good enough to get started. Of course, if you want to do more fancy stuff, you may need things. For example, if you want to denoise things, you send some data, you have to have denoised data at the output so that your system learns how to create that kind of denoised data. Anyway, so what is the auto-encoders? Auto-encoders, basically encoder and decoders, and it always has two parts, data. You compress that into smaller dimensions. Some literature call that compressed representation. Some literature call that as bottleneck. Bottleneck in English language has got negative connotation, but in machine learning language, bottleneck has got no negative connotation. It just means compressed version. Now you can have a decoder that will recreate the data as it is. Right. One caution, even though the dimension here is smaller, these are not really good for compression. You can't just use this naive autoencoder to create a compression algorithm that can beat JPEG or MPEG, something like that. That being said, yes, you can do that, but you just have to add extra measures. You have to add extra steps in the process so that it can still do compression. And in fact, when you design the architecture for compression, same autoencoder architecture can be designed. They actually beat the conventional JPEG and MPEG and so on. N. So these are very compressed slides. So that is why I have shared the sources of the slides as well as I'm passing through. Okay. There are lots of applications of this kind of network autoencoder. So you can use, you can once train it and use the encoder part and decoder part separately. And we have used that for sensor calibration, sensor blind calibration, extremely versatile and powerful tools. And one of the application is super resolution. So I've given a Jupyter notebook for super resolution. And the lab exercise for this week is that just pick up any EO image and try to apply this super resolution algorithm and see if it actually works or doesn't work. You know? And then how can you improve the results. Now, the standard autoencoder is good enough, but it is not really good in creating data. So the generative part I just discussed, this naive encoder decoder, it's good at doing certain things, compressing things and denoising things, but they're not very good at being generators. So generative, for example, what do you mean by generative machine learning? So let us say I have studied a bunch of data and I have plotted the histogram and I found that okay, they follow a Gaussian distribution of mu or mean 2 and variance 10. Once I know that, I can put that to a simulation, and if I simulate a bunch of numbers created from Gaussian distribution of mean 2 and variance 10, I can create thousands of data. And all the thousands of data are all new data, but they follow the same generative model that has been followed by the small amount of data that I started with. So I start with some data. I understand the generation process behind it. Once I have modeled, I can use that to create new data. Now, this so far is not good enough to create new data. So it needed some tweaking, and that is what is called variational autoencoder. So when can it be assumed to be creating new data? If in this compressed representation, once I've done this thing, I split this part. The decoder is separated, and I should be able to give any random number with some seed value, and that should be able to create new data of the same kind. If that can be done, then that is a generative. So one requirement here, this compressed data that I am creating by this autoencoder training, that okay, one requirement is that it has to be low dimension. The second requirement is that it has to be as close as possible in distribution to Gaussian distribution. So if I can make this compressed version follow a Gaussian distribution nicely, then I can separate the decoder and create any number using the same Gaussian distribution, and it will create new data. Hence, in addition to the first requirement while training an autoencoder is that you make sure that what you are creating here is same as the input. So you find the error between input and the recreated image or data, and you try to minimize the error. In addition to that, you enforce another requirement. The other requirement is that the distribution of the compressed data representation has to be as close as possible to Gaussian distribution. Now, if you remember, we just mentioned how to find the difference between two distributions. We can do that by using KL divergence. And that is your variational autoencoder. In variational autoencoders, you enforce the bottleneck representation to follow a Gaussian distribution as much as possible. Okay. Yeah, let me just KL divergence, and this is a snippet of the code just showing the two different loss functions. So you have now two loss functions. One is the reconstruction loss, which is the difference between the input and the output, and second is the KL divergence loss. And then you together they make one loss, and when you minimize that loss, you make the representation good, as well as you make the bottleneck data as close to a Gaussian distribution as possible. Right. Now, just having this is not good enough, because if you are trying to create images of digits, and you have got all the digits 0 to 9, then it's difficult. Like when you are generating, how do you make sure that it is generating the digit that you want it to? Otherwise, if you just generate any random digit, so that can be solved by what is called conditional VAE. In addition to the input, you also input what digit it is, and that is by a one hot encoder kind of thing. Again, nothing too complicated. Once you understand the concept, it's not that difficult. These are like images created by VAE, and you can see that they look quite natural. And of course, if you can create images, nothing stops you from creating music, and that's an example of music VAE. They can use that to create music as well. Now, all well and good. The next thing is, okay, you can have a Gaussian vector, and then it can, you can train networks, and it can create some kind of data. Now, to make the data even more, okay, for something simple like digit, that's a simple thing. It's easier. But for something more complicated, like for example, optical image or even EO images, they have got so many things going on. Simple VAE is not enough. It is not able to do the job. So you need another layer, and that is where generative adversarial networks started becoming popular. So they have got two parts. The first part is simple VAE decoder. So it has got, the input is random numbers, and you have got the neural network, and it creates some kind of data. There is a second part, which is a discriminating neural network, which distinguishes, okay, what is the class of this input that has been created? Is it similar to the image that we are expecting? So it discriminates, okay, yes or no. If it says that it doesn't match, then there is an error. That error is taken back to train both this part and this part. And it goes on iteratively till your discriminator cannot distinguish between the original image and the image that has been created by the neural network. Easy to understand, and then even you can look at the code. The code is not very complicated, but it's the concept. It's very strong, and it has really revolutionized a lot of the AI things that we see now. Just some example, like pictorial representation of how it slowly starts training. So in the first attempt, it might look something like this, and then 4 attempts something like this. But the discriminator output is still doesn't say that it looks like a cat image. Not till. But when it starts creating something like this, discriminator says yes, it's indistinguishable from a cat image, and that's when the whole thing is frozen, and then it can start creating high fidelity, high definition images. Now, transform model, this again, it requires a full course on its own. So we have seen the whole revolution, right? We have starting from your encoder decoder, and you take the decoder part, and now suddenly neural networks can generate new data. And then we have seen auto-encoders and GANs. Now, when you are using similar principles to create time series, like for example, your large language models, then what happens, one issue that came into picture was that while creating time series, they tend to forget what's going on. So the transform model came where there was a seed value on where to focus. And the original transformer paper, the title was quite non-technical and interesting. It says attention is all you need, and that was the introduction of transform model. And transform model has really revolutionized the whole AI field. All the large language models have transformers and in their core. One last architecture for this part is UNet. So UNet is you can see it looks very similar to encoder decoder. So it's one of the members of the broader family we can call encoder decoder networks. The difference is that in a simple encoder decoder, the encoder part is a neural network, the decoder is a neural network. But in UNet, the encoder part has got bunch of convolutional neural networks, so it can extract features. And the decoder part has also got CNNs. It is recreating the original data. Now, once you put into this kind of way, you are not just compressing. You are actually compressing and finding the relationship between the different data substructures. That is quite interesting. And one of the work that I did a while back was creating ice chart. Ice chart is basically the thickness of ice in an ocean from Sentinel-1. And so the input to the unit was the Sentinel-1 radar data, and the output was an ice chart. So every pixel would have a number that will say, okay, what's the expected percentage that part has become ice. So yeah, so that's the end of this part. Let me quickly show the course in action. Where is that? Let me give me a second. Am I still audible?
Yes, we can hear you.
Yeah, perfect. Let me share my screen and share code with principal component analysis. Yeah. Okay. What's going on now? Oh no, 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 no. Oh, why? Okay. Right. So I've shared this thing in our teaching system as well. So I hope you can access this one. If not, let me know. So again, some basic PCA, kPCA kind of examples. The main idea why I shared the code is because we have discussed the steps behind creating PCA, right? But in reality, you don't really have to take all the steps, because most packages have got ready-made commands or functions for PCA. So scikit-learn, sklearn has got PCA, kPCA commands very easy to use. So we'll take a data set that looks like this, right? Now, if I want to compress this into, because I'm looking at from the top view, right? So I can see that there are two groups of data. That's easy to see. But if I'm trying to look from one dimension, so on one dimension means you can only look from this side or some other side. So this data is interesting because no matter what angle you look at the data is always overlapping on each other. So when we do principal component analysis on this data, this is basically to show the limitation of PCA. So PCA is good, but for something like this, it doesn't really is not able to show that there are actually two classes. So let's so this is how PCA you run PCA, and in 2-dimension same data structure is retained. It just has slightly changed it. It's like orienting that slightly. But when you put 1 dimension, it's like you are looking at it from one angle. And again, there's overlap happening here. Now, kPCA, if you remember what kPCA does, kernel PCA, it processes the data in a higher dimension. And many times, intuitively speaking, it's like you taking this data and like stretching it out to separate them out. So this one, if by some way I could stretch them, I could like snatch them from each other, then I would be able to see that there are two classes. And we'll see what happens when you apply kPCA. That's exactly what happens. Because kPCA deals things in a higher dimension, it's literally like snatching them apart. And you can see that now in 2 dimensions, they look quite separate. And of course, in 1 dimension also, they will look separated. Now, okay, there's another kind of data set, again, very difficult because this is one blue color bunch of data embedded inside a red color. At least in the half moon data, there is some separation you could see. But in this kind of data, if you look from 1 dimension, from any angle, there is no way any separation will be visible. So you do PCA, they completely overlap. And you do kPCA, it literally snatches them out. And it shows that they actually are two different bunch of data. But again, kPCA, anything more complicated will have more parameters. So you can see that there are a couple of parameters. There is component is there, yes, but there are two other extra parameters. There is a kernel, what kernel you want to use, and there is the gamma parameter. For kernel, a thumb rule is that you use RBF, which stands for radial basis function, but it's not guaranteed that it will work all the time. So it's advisable that you try a couple of kernels just to be sure that you are getting the best deal. Now, okay, this is more complicated. This is called Swiss roll data. It's a couple of different classes like rolled with each other. Looking from 3D, you can see yes, there are like different classes actually very well separated. But if you try to visualize from 1D or 2D, it's next to impossible. But this is where we see, okay, PC, of course, it cannot do anything, it is all jumbled up. And yeah, kPC also, at least the RBF was not able to do. But then again, you can play around and see if any other kernel and some other gamma can make it look separate. Now we'll come to the algorithms that have been developed only for visualization, like locally linear embedding, LLE, TSNE, etc. So you apply LLE and you see how beautifully it has separated them out. So it has like traced them out. And because your goal was to preserve the structure in that thing, and by preserving the structure, you can see that yes, the data is actually, there are a couple of classes here, they are well separated. So once you see that, you get the confidence that okay, now I can develop some algorithm for the data classification. At least structure wise, it is separated. So now it's up to me to find all kinds of fancy algorithms to do the separation. And there is another called MDS. It doesn't do much good. And then there is TSN. TSN is one of the most powerful visualization tools. And this is what it does. Again, there is no guarantee which one will work good for you. Sometimes TSNE works better, but in this particular case, at least your simple LLE is working better. So yeah, that brings me to the end of this lecture. Are there any questions?
I think everything's clear.
Thank you. I have recorded the video. I will upload them into our system as well. And yeah, I've also released the last assignment. Please attempt the assignment because they are marked. And yeah, if we don't meet before holidays, Merry Christmas and Happy New Year.
Thank you, and
Thank you.
Merry Christmas to you too.
Thank you. Bye.